Everybody, this is part 2 of the 4.2 day 2 notes where we're looking at the second derivative test and concavity with functions. So in the first example we're going to look at here says determine the points of inflection and discuss the concavity of the graph. All right, so what we're going to do is we want to make sure we know the connection between the points of inflection, concavity, and the second derivative. So points of inflection are going to occur when the second derivative of a function is equal to 0 or undefined and changes signs. And that changing signs is key. So let's start by taking the first derivative of this function, which we should be able to do pretty easily with power rule and sum or difference. So the first derivative is going to be 6x squared minus 6x minus 12. And then from there we'll go ahead and we will take the second derivative of the function, which is simply the derivative of the first derivative. So that's going to give us 12x minus 6. Again, we want to know when this is equal to 0 or undefined. So looking at that equation, we should all recognize that as a linear function, which is always continuous. So it's never undefined. We can factor out a 6, and we have 2x minus 1. So the only possible point of inflection is going to happen at the 0, 1/2. Now, x equals 1/2 is a possible point of inflection. In order for it to actually be a point of inflection, there has to be a sign change in the second derivative at that value. So what we're going to do is we're going to go back and we're going to make an alt table, but this time we're going to use the second derivative. So we're going to look at from negative infinity to 1/2 and 1/2 to infinity. We're focusing on the second derivative. So I always like to write that f double prime there so I know we're doing the second derivative, not the first derivative. And if we look in the factored form right here, I know that 6 is positive, so the sign is going to really be dependent on what's going on here. If it's positive, you end up with a positive second derivative. If it's negative, you end up with a negative second derivative. So, 0 is one of those values that's from negative infinity to 1/2. So 2 times 0 would be 0. 0 minus 1 is negative 1. Therefore, you're going to have a second derivative that is negative at that point. If we plug in a number greater than 1/2, let's say 1, 2 times 1 is 2, minus 1 is 1. Positive 1 times 6 is positive 6, so the second derivative is going to be positive at that point. So what that now tells us is that 1/2 is a point of inflection. All right? So there is a point of inflection when x equals 1/2. So we can abbreviate that as pi. If we wanted to know the actual coordinates of the point of inflection, the x coordinate's 1/2. If we wanted to find the y coordinate, we would have to plug back in to the original function. So we could do that real quick. F of 1/2 is going to be 2 times 1/2 cubed minus 3 times 1/2 squared minus 12 times 1/2 plus 5. All right, so here we're going to get 2 times 1 over 8 minus 3 times 1 over 4 minus 6 plus 5. So this is going to be 1/4 minus 3/4. And negative 6 plus 5 would be negative 1. If we get a common denominator, that's going to become negative 4/4. So we have 1/4 minus 3/4, which is negative 2/4, minus 4/4 is negative 6/4. And that simplifies to negative 3/2. So the point of inflection is at 1/2, negative 3/2. The other thing we were asked to do is discuss the concavity of the function. So the sign of the second derivative is always going to determine the concavity of the function. If the second derivative is negative, the function is concave down. And if the second derivative is positive, the function is concave up. So we can formalize that and say f of x is concave down on the interval negative infinity to 1/2. And if you wanted to give an explanation, we could say because f double prime of x is less than 0 on that interval. We would then also be able to say that f of x is concave up on the interval 1/2 to infinity because the second derivative is greater than 0 on that interval. Oops, it's supposed to be positive 1/2 to infinity. So we identified the point of inflection. We discussed concavity of the function. Again, there's always going to be that connection between the second derivative and points of inflection and concavity of the function. All right, the next situation we have is what's called the second derivative test. Let f be a function such that f prime of c equals 0 and f double prime exists on an open interval. If the second derivative, so f double prime of c, is greater than 0, then f has a relative minimum at c f of c. If f double prime of c is less than 0, then f has a relative maximum at c f of c. And if f double prime of c is equal to 0, then the second derivative test fails and nothing can be concluded by that test. In that instance, you're going to want to use the first derivative to make a decision about the critical value. So let's see how that can apply to this example. So we have a function, all right? And again, we're talking about critical values, but also what is the value of the derivative at that critical value. So we can start by taking the derivative of the function, f prime of x. We can apply the power rule, so we're going to get 12x cubed minus 6x squared. To find critical values, we want to set that equal to 0. So I'm going to go ahead and factor out the greatest common factor of 6x squared. And then that's going to give us 2x minus 1. So we end up identifying that critical values are going to be 0 and 1/2. So critical values are x equals 0 and x equals 1/2. We're trying to use the second derivative test to determine if that's a relative minimum or relative maximum. So that's how we're going to go with this problem. So the next step would be to take the second derivative of the function. Again, apply the power rule again. So we are going to get 36x squared minus 12x. All right, so what we would then go ahead and do is evaluate the second derivative at each of those critical values. So f double prime of 0 is going to be 36 times 0 squared minus 12 times 0, which is going to equal 0. All right, so what our test above told us is that if the second derivative at c is equal to 0, then the test fails. So for this, the test fails, and we don't know, we can't determine anything about the relative extrema at that point. If we then evaluate f double prime of 1/2, we're going to have 36 times 1/2 squared minus 12 times 1/2. That's going to be 36 times 1/4 minus 6. So 36 times 1/4 is 9. So 9 minus 6 is 3, which means f double prime of 1/2 is 3. And again, what we're trying to do in this situation, guys, is determine, does the function have a relative minimum or relative maximum? So our second derivative is greater than 0, which means it's going to fit the first case where the second, f double prime of c is greater than 0. That means we have a relative minimum. So what we're able to determine from the critical value at 1/2 and seeing that the second derivative of 1/2 is 3 is that f of x has a relative minimum at the point 3, comma, and if we wanted to find the actual minimum value, we would plug in 3 to the original function. So if we do that real quick, f of 3 is 3 times 3 to the 4th power minus 2 times 3 cubed minus 1. 3 to the 4th power is 81 times 3, that's 243. 3 cubed is 27 times negative 2, that's going to be negative 54 minus 1. And that's positive 188. So f of x has a relative minimum at 188. So at the point 3, 188. Now, some people might be thinking, well, why is it a relative minimum if the second derivative is positive? Well, to make sense of that, you have to think about what that's telling us about the function. Is when the second derivative is positive, that means that the function is concave up at that point. So that critical value is going to be this value right here, which is a minimum. Now the alternative for finding a relative extrema is to just use the first derivative test, right? And we have the interval negative infinity to 0, the interval from 0 to 1/2, and the interval from 1/2 to infinity. And we're looking at that for the first derivative. So we would be looking for sign changes. Now, 6x squared, that's always going to be positive. So to determine the sign of this, it's really going to depend on the 2x minus 1 again. So if I plug in a negative number, 2 times any negative number is negative, minus 1 is going to be a negative number. So that's going to give us a negative value. If we plug in a number between 0 and 1/2, say 1/3. So if we plugged in 1/3, we get 1/6, or sorry, if we plug in 1/3, we get 2/3 minus 1, which is a negative number, so that's going to be negative. And then if we plug in a number that's larger than 1/2, say 1, 2 times 1 is 2, 2 minus 1 is 1, so we have 1 times a positive number, which is positive. So if you think about what's happening to this graph, a negative derivative tells us the function is decreasing. Well, at 0, the derivative still stays negative, so it continues to decrease. And then once the first derivative is positive, our function is increasing, so it's going to increase. Therefore, the only extrema is going to happen right here, which is a relative minimum. So there is no extrema at 0. Second derivative test failed. All right, but we could use that first derivative test to in fact verify that there's neither a relative min or a relative max. All right, guys, that's going to do it for part 2 of the notes. We will continue the other examples in part 3.